Hi everyone, here's Ned Koch for MIS5390. This is the second video for week 5 of the course. So we have an individual assignment, which is a commentary by 1 p.m. on Friday this week. There is already one commentary there. Thank you very much. Today I'm going to talk about the English language and the models used project. And let me show you what I got, my analysis. So very different from the one you gave me, but this analysis meet the requirements of the course. So we have 1, 2, 3, 4, 5, 6, 7, 7 variables. Let me show you how I got to this model. First, let me close out of here and open your the model that you sent me, and then point at some problems with that model, and then I'll show you how I got to this one. Okay, this is what I got from the team, and there is one key problem here that is a telltale of or a red flag in connection with collinearity. It's these two path coefficients here. They are, in absolute terms, they are greater than 1. And this is an indication that there are problems with the analysis. And the problem comes from the fact that these two variables, they have little variation in them. So just 0 and 1, and that they are somewhat collinear with one another. So there are too many rows where you have zeros and you have ones. So in other words, these two variables, they don't have enough variation, and the variation is partially collinear. So that leads to these path coefficients in absolute terms greater than 1. This is a problem. It's a telltale sign of problems. And this is, I even have seen professors and data analysts having this type of thing in their models, and they don't realize that this type of thing, it's like the results are completely distorted because of this. So this is a telltale sign of problems. Having said that, from a measurement perspective, let me see loadings and cross loadings. So the variables that you aggregated indicators for, the loadings are high for them, this 1, 2, and they are of the same sign. So the measurement model is okay, but so it passes convergent validity. Let me see, latent variable coefficients. It passes convergent validity. It passes reliability, right? The composite reliability and the Cronbach's alpha are high. So this model looks good from a measurement perspective. Let me take a look at the correlations. So all values here are lower in absolute terms than the one in diagonal. So it actually passes discriminant validity. From a measurement perspective, the aggregations you did here in these two variables are not a problem. But the problem is that then you have only 5. And I said 7 for an A-level project. Now you may say, well, but I have 3 here and 3 here, so it adds up to more than 5. The problem with that is that you are aggregating them, but individually they provide interesting insights as long as they are not collinear with other variables. And so having them separate provides a more interesting, more complex, more insightful analysis. And of course, I had to do something about this. So let me tell you one thing that I did here. So I changed the data set. So I got your data set here, and then I just created a new categorical variable. because you have two columns, model A and model C. So model A being 0, model C being 0, I assume that it's model B then, right? So this row here refers to model B. And model B is, let me see in your description. So model B is Texas, model A, Massachusetts, model C, New Jersey, New York. So what I did was to create another categorical variable, not numeric, categorical, and it has like the three models here. Model B, when you have 0, 0, model A with 1, 0, and 0, 1, model C. And then what I did was I selected this variable. I did a Control C here. And then I went to modify, add labels from clipboard. Then I chose OK. And then I just followed the wizard, clicked finish, and then the software read that categorical variable as a data label. Now, one thing you should know is that you can only do analysis, model-driven analysis, which are based on calculations of coefficients of association. You can only do them with numbers. You cannot do them with text, with a categorical variable like this one. So what you have to do is to convert these categories, model B, model C, model A, to numbers. And since you have more than two, you cannot dummy code them as 0 and 1. You have to let the software make the conversion. And I did this, and first of all, I just separated all of the variables. I'll just show you briefly what I did here. I just went here to the model, cleared the entire model. And then I added the variables one by one, and I gave them names. So for example, grad rate, and I did this for all the variables. So I'll just go back to the model that I was showing you before, the model that I generated. Okay, so let me open that model. So this is the model that I created and the results. I'll talk about the results in a little bit. But okay, so how did I convert that categorical variable to numeric? I went to the option Explore, Categorical, Numeric Categorical Conversion. And then I clicked on Categorical to Numeric. I chose that categorical variable model. And then I got these numbers here, right? Ignore this because I already created, so it's actually highly correlated with itself. But if you ignore this one, and that's what I saw before, you can see that that categorical variable is strongly associated with presence and retention. And these are variables that I named them as presence and retention, but I'll show you what they really are there. But model, therefore, I created model, the variable model, anchored on presence and retention. And since these are positively correlated with graduation rate, I chose the links here. When I chose that, I chose the signs as positive. But I'm not going to do that because I already created that variable. So I'll just stop right here. So I already have model created, and I did the creation in that way. Okay, so what is this model telling me? First of all, let me show you the relationship between model and retention and model and presence. And this is the relationship that ends up affecting graduation rate indirectly. So model affects graduation rate positively and indirectly through retention, and model affects graduation rate indirectly through presence. Let me show you what the indicators that are used here. So for presence, I actually use chronic absence reversed, right? I assume that your R here means you reversed that variable. So instead of using chronic absence R or something like that, or no absence, I just called it presence. And dropout rate reverse, I called retention. Okay, so let me show you something interesting here. It's probably the most interesting finding, at least from my perspective, maybe from yours as well. It's the relationship between model and retention. So here I will go to View, Relationship Graphs with Data Points and Legends, Multivariate Relationship, or I'll choose the bivariate relationship, Unstandardized Scales. And then I'll go to Settings, and I will choose the data labels to be shown, and I'll choose the model data labels. And here's what I have. Okay, so the scores that the software gave to model were these here. Minus 0.7, let's say close to minus 0.3, and 1.5. So as you can see, the scores go from minus 0.7, low, and that's Model C. That is New York and New Jersey. And Model B is Texas. And Model A is actually closer to, that's Massachusetts, is closer to New York and New Jersey than to Model B. So Model B, Texas, is far to the right, and it is associated with the highest retention levels. So Texas far ahead of New York and New Jersey and Massachusetts in terms of retention. And you see the same thing happens regarding presence. So you go to the same graph that I shown before, show the same settings. So again, you have a little bit different distribution of points, a little bit different scores, or no, the scores are the same for model. So again, Texas far ahead in terms of non-absence or presence, far ahead of Massachusetts and New Jersey and New York and Massachusetts in terms of the model that it uses. So this is an interesting finding. The indirect effect here is the product of these two coefficients. So the product of these two would be 0.21, and the product of these two is a little lower. I actually calculated here. It's 0.179. So this influence here through retention is stronger than this one. In other words, Texas is adopting the best model. And that model has a stronger impact through retention on graduation rate, which is my main measure of success here, and a lesser influence on graduation rate through presence, but both are significant. The R squared here, I would say an R squared greater than 0.2 is desirable. This is 0.4, so it's explaining almost half of the variance in graduation rate. Now, what are these variables in the middle telling? And I don't think it's reasonable to assume that the model causes them. It's more likely that they cause the choice of model. So a higher Hispanic higher Hispanic rate, higher poverty, higher enrollment seem to favor Texas, the model in Texas, because they're all positive, and this variable, it actually increases as you move from New York to New Jersey, then Massachusetts to Texas, but Texas is the highest. So positive here means more likely that you have Texas here. And in terms of graduation rate, so Hispanic, lower graduation rate, right? So more Hispanic, lower graduation rate, more poverty, lower graduation rate, more enrollment, lower graduation rate. I guess this one could be explained by having more students, and more students, you have more people to manage, maybe a lower or a higher teacher to student ratio, more students to manage with not as many staff. So that could be the reason for this impact. It's the least important of these three. These three I don't think are caused by the choice of model. I think they are actually predictors of the choice of model. And in this model that I developed, I have the model, the English learning model, influencing retention and then graduation rate, and model influencing presence and graduation rate. If you go to correlations among latent variables and errors, you see that graduation rate has a very low correlation with model. So model does not seem to influence graduation rate directly. It influences it indirectly. Now, if you want to know the strength of that influence, you can go to View Indirect and Total Effects, and then look at total effects, which are at the bottom of this table. So the total effects of model, the total effect of model on graduation rate is 0.391. So it's a pretty strong total effect. It's almost as strong as the direct effect of retention on graduation rate. So all of this actually supports the idea that the model that is being chosen by Texas, which is this one here, and is superior to the other two models, this one employed by Massachusetts and this one employed by New Jersey and New York. So I think these are interesting findings. If you agree with this model, you're good to go. You have all the elements here for an A-level project. Congratulations. I find this interesting. I hope your client organization will find it interesting. So now I suggest you go ahead and start, if you agree with these results, right? You're welcome to make changes in the model. But it looks to me like this is a pretty good model. In any event, I will share the project file with you. I will share that modified data set with you. So it's just go ahead and start writing your report. Well done, both teams. Well done. I think interesting projects, as I said, for the other team, not finding that something you expected to have an effect, not finding an effect, is in and of itself an interesting data analysis discovery. So this one, I guess, could potentially be more exciting for the client organization, because often the client organization, they want you to confirm what they already think they know. So this one might be a confirmation. The other one, I don't know about the strength though. Maybe this is stronger, than they would have expected. The other team is might be a bit of a disappointment, but if you are planning on making investments based on previous beliefs, that's a good thing. You're getting maybe bad news, because then you're not wasting money. And depending on the scale here, it could be millions, potentially even billions of dollars for very large companies. So well done. This is what I have for today. Thank you for watching.